The next phase of regression analysis is called residual analysis or model adequacy checking, in which the appropriateness of the model is studied and the quality of the fit is evaluated. The outcome of adequacy checking may indicate that either that the model is reasonable or that the original fit must be modified. So the regression analysis is an iterative process. Residual analysis helps us to check the validity of assumptions when fitting a linear regression model. Furthermore, checking residuals is a way to discover new insights in your model and data. Graphical analysis of residuals is a very effective way to investigate the adequacy of the fit of a regression model and to check the underlying assumptions. Let's see how to get the residuals of the fitted model. Residuals are an observation level statistics because each and every observation there's an associated value. We can use augment function to extract observation level statistics of the model. Observation level statistics are the informations about individual observations. The augment function outputs observation level statistics into a tidy data frame. Now each row is an observation from the original data. Note that new column names start with dot. Dot row names, dot fitted, dot sc, dot fit, dot this is for residuals, dot hat, dot sigma, and so on. Each row in an augment output matches the corresponding row in the original data. If the original data contained row names, augment returns them into a column called dot row names, like this. And again, newly added column names begin with dot to avoid overwriting columns in the original data. This is the visualization of the model. And let's draw residuals on top of it. The model residuals represented by the red vertical line segments in the plot. The difference between the fitted value and the observed value. Residuals show how far each case is from its model value. Blue line shows the predicted values. Black dots show the observed values. These are the assumptions we made about the regression fit. First, the relationship between the response and the predictors is linear. The error terms are assumed to have zero mean and unknown constant variance sigma squared. Errors are normally distributed. Errors are uncorrelated. Taking together the last two assumptions, errors are normally distributed and errors are uncorrelated, imply that the errors are independent random variables. Now we are going to use residuals to check the validity of these assumptions. Graphical analysis of residuals is a very effective way to investigate the adequacy of the fit of a regression model and to check the underlying assumptions. First, we are going to test the assumption the errors are uncorrelated. If the data are obtained in a time sequence, a residual versus ordered plot helps to see if there is any correlation between the error terms that are near each other in the sequence. The plot is only appropriate if we know the order in which the data were collected. If the data were collected over time, residuals should be plotted in time order to determine if there is serial correlation. For example, let's say you have one variable x, that's year, and your y variable is total number of sales in each year. Now you have a time factor. So when you fit a regression model, sales versus year, now you need to plot the residuals of that plot in a y values residuals and x-axis time order. It's like a time series plot of residuals. If you observe a pattern, then you can say the errors are correlated. If there's no pattern, or if the points are random, then you can say the errors are uncorrelated. Often we can conclude that the correlation assumption is sufficiently met based on a description of the data and how it was collected. If there is no time variable in the data set, then you can check if this assumption is sufficiently met based on the description of the data and how it was collected. That means you need the knowledge of study design or data collection in order to determine the validity of this assumption. Here, our observations are different types of occupations in Canada. We assume that one occupation does not depend on the other. So, based on that, we assume errors are uncorrelated. Next one is residuals versus fitted values. We discussed this earlier. This is useful for detecting several common types of model inadequacies. There should not be distinguishable pattern in the residual plot. That is, residuals should be randomly scattered. A non-random pattern such as assumptions might be violated. Here I plot residuals versus fitted value. This is the data frame that I obtained from the augment function. So this one here, output of the augment function is a data frame, and I have fitted values as well as residuals here. So I can use this as the input to the ggplot function. My x variable is dot fitted, y variable is dot resid. In order to obtain this graph, you need to complete the next two lines. So basically you need to add point layer, geom underscore point, as well as you need to add another geometric layer in order to specify this horizontal line. So this plot is used to diagnose violations of homogeneity of variance, linearity, and zero mean. If homogeneity of variance is violated, or the constant variance is violated, the assumption of constant variance is violated, the standard error estimates associated with the regression coefficients are no longer entirely reliable, and your t-tests for coefficients aren't quite right either. We can see from this plot here the average of residuals remains approximately 0. Residuals contained in a horizontal band indicating constant variance. Here I plotted residuals versus predictor, that's education in this example. X is education and Y is resid. Plotting the residuals against each of the predictor variables is also useful. In simple linear regression case, it is not necessary to plot residuals versus both fitted value and the regression variables because both of these plots are the same. But in multiple linear regression analysis, you need to plot residuals versus predictors. Furthermore, it is also good to plot the residuals against any predictors that are not in the model. If any of these show a pattern, then the corresponding predictor may need to be added to the model. It is important to keep in mind if you stare at a scatter plot of completely random points long enough, you will start to see patterns even when there are none. Residual analysis should be done thoroughly and carefully, but without over-interpreting every slight outlier or anomaly. Serious problems with the linear regression model generally reveal themselves pretty clearly in one or more residual plot. Next, normality plot of residuals. So examine the distribution of the residuals. It is important to examine the distribution of residuals in order to determine if the errors are normally distributed. We can plot the residuals in a histogram and normal QQ plot to visualize their distributions and assess normality. Most inference methods for regression are robust to some departures from normality. However, it is important to check the assumption of normality of residuals. Here, the residuals look very close to being normally distributed. I could also run a Shapiro-Wilk test to check whether the assumption of normality is satisfied. You can use the function Shapiro.test, and here you need to pass the residuals of the model. Here in this hypothesis testing, the null hypothesis is the errors follow a normal distribution. The alternative, or the H1, is the errors do not follow a normal distribution. Here, since p-value is large than 0.05, we do not reject H0 under 0.05 level of significance, so we do not have enough evidence to say errors are not normally distributed. So the normality assumption is satisfied.